ମୁଁ କେବେ କିଛି ଖେଳି ପାରିବିନି। ମୋର କଣ ଦେଖିବ ତମେ? ମୋର କିଛି ଦେଖିବନି ନା। ଆମେ ଭଲ କ୍ରିକେଟ।
Hello, sir.
Hello, hello.
Dr.
Am I audible?
Yes, sir.
Yeah. Okay.
So if you can share your screen, sir, so that we can test if there is an issue.
Yes, sure.
Okay, sir.
Okay. Are you able to see my screen in full?
Yes, sir.
Right? Okay.
So
Perfect.
we'll begin sharply at 6.
Sorry, I didn't get that.
So we'll begin sharply at 6 p.m., sir. Let's all the
All right,
participants
all
join.
right, all right, all right. I'll wait until then. Yeah,
Thank you, sir.
yeah.
What Good evening, everyone. We warmly welcome you all. We warmly welcome you all to the fourth day of the Atal Faculty Development Program on Green Horizon. We would like to thank you, all of you, for your enthusiastic participation as we continue this academic journey together. We are glad to have with us as we explore new dimensions of wind energy and grid integration. Our first session today, we have Dr. Royston Vijay Castillo, Manager of R&D, Ola Electric, Bengaluru, who will speak on next generation wind energy systems, innovations for climate smart power. Dr. Castillo has earned his BTech in Electrical and Electronics Engineering from Srinivas Institute of Technology in 2015, where he was recognized as the best outgoing student and top performer. His BTech project won the KSCST Project of the Year Award and the Gandhian Young Technological Innovation Award 2016 at Rashtrapati Bhavan. He completed his MTech in Power Electronics and Drives from NIT Mizoram, reaching the quarterfinals of the Texas Instruments Innovation Challenge and presenting at the 4th Global Exhibition on Services. He has earned his PhD from NITK Surathkal, contributing significantly to the renewable energy generation research. With 5 granted patents and numerous publications, Dr. Castillo has secured a DSC grant of 51 lakhs for developing a lab-scale renewable power and emulsion system. Since 2023 July, he has been the manager of R&D at Ola Electric, Bengaluru. We thank Dr. Castillo for joining us for the session. So please.
Yeah, thank you so much for the brief description about me. So let's get started. Let me share my screen. Okay. Is my screen visible to everyone?
Yes, sir.
Okay, okay. So welcome to this presentation on next generation wind energy systems, which is an interdisciplinary innovation for climate smart and sustainable power. I am Royston Castellano, currently working in Ola Electric as a manager in R&D team. So I primarily work on vehicle-related, EV-related products right now, apart from wind energy. Wind energy was my PhD project, and I've also done kite-based wind power generations, which is airborne wind technology in the wind technology itself. But today we'll explore what is the cutting-edge technology in wind power systems and what is this interdisciplinary approach and how AI is jumping in to have a sustainable power. So wind energy has grown into one of the most important tools for decarbonizations. Basically, globally, more than 1.1 terawatt of wind capacity are installed. So, according to IPCC, which is a international body, has made it clear that emission must fall by 45% by 2030 to keep the global warming to just 1.5 degrees Celsius. So, so today I'm going to explain you. This is my presentation overview for the day. So this slides outlines our roadmap for today's discussion. So we begin with global context, setting the urgency of renewable energy expansion in the face of climate change. Next, we dive into turbine technology, innovations, ultra lightweight composite blades, biomimicking aerodynamic designs, modular turbines, floating offshore platforms that open vast new resources. The third section covers interdisciplinary innovation, how nanotechnology, digital twins, and AI-driven predictive systems combine to enable breakthroughs in wind power. And further, we'll also discuss climate smart systems, where turbines are engineered to withstand hurricanes and operate in Arctic conditions and adapt to seasonal weather patterns. So fifth is sustainable integration, hybrid systems combining wind, solar, and storage, grid farming inverter for stability and circular economy in strategic development of to cycle turbine materials. Finally, we look into future directions and highlighting the most transformative research areas and strategic recommendations. So this is roadmap is not just theoretical. Projects like Equinor High Wind in Scotland, the world's first floating wind farm, so how engineering and interdisciplinary approaches combine deliver to a real world solution. So we'll just go through it and you'll understand what is happening around the world in wind technology and think of this as our compass through the presentation. So coming to the global wind energy landscape 24-25. So globally, wind energy reached 1,173 gigawatts of installed capacity in 2024, growing at an annual rate of 11.5%. This growth is majorly led by China, which contributed nearly 72% of the new capacity additions in 2024 alone. Such scale demonstrate what coordinated policy, investments, and manufacturing can achieve. So the offshore sector is particularly promising, expected to grow from $4.9 billion in 2024 to $6.6 billion in 2025. So offshore projects like Hornsea 1 and 2, one of a kind project in UK, supply millions of homes, proving that utility scale offshore wind turbine is now a reality. So costs have been dropped dramatically from 55 cents in US dollars per kilowatt hour in 1980s to under 3 cents in US dollar today, making wind one of the cheapest power sources globally. Projections suggest that global capacity will triple by 2030 under current policy frameworks. So the challenge is no longer cost alone. So it is integration, durability, and resilience. For example, such as Texas, where grid failures highlighted variability risks, show that the system level solutions are critical. This presentation sets a scene where wind energy has achieved scale, but to fulfill its promise, we must innovate and integrate smart than ever. So climate change and renewable energy urgency. So why it is urgent right now? So this slide underscores why urgency is central to this discussion. The IPCC has warned that to keep the global warming below 1.5 degrees Celsius, greenhouse gas emission must be reduced by 45% by 2030. So that is just few years away, right? Wind energy could supply up to 35% of global electricity by 2050, but current technologies are not yet sufficient. So variability, grid challenges, and durability issues remain. Without rapid innovation, we risk missing climate goals. So real world impacts are already visible. Stronger storms are coming in from the Atlantic. Record breaking heat waves are coming in the Europes. And floods in Asia are disrupting lives and energy systems alike. We have seen in the news in recent times the floods have been coming. It is one of the side effects of the climate change. So coming to wind energy, at the gigawatt of wind capacity by 2030, alongside broader renewable goals, which is set by the agencies. So this urgency is not abstract. Communities from Puerto Rico to Bangladesh are already face this climate-related power disruptions. So resilient and adaptive and sustainable wind energy systems are needed to safeguard both energy security and climate. Coming to why an interdisciplinary approach is required. So wind energy innovation requires multiple disciplines conversing. So basically, we need many disciplines to come together and form an idea around the wind energy technology. So engineering remain the core. Structure and mechanical design ensures turbine withstand these stresses, and material science contributes composites like carbon fiber, enabling blades that are longer, lighter, and more fatigue resistance. So data science and AI optimize turbine performance, providing predictive maintenance and real-time adjustments. So atmospheric science ensures accurate forecasting and it integrates wind resources assessments into operations. And economics and finance create a framework for scaling up this wind technology. So what are the key challenges we are facing in the wind technology? Even as the wind energy scales, challenges remain. So first, intermittency. So wind does not blow consistently, right? Creating stability issues for grids. So advanced forecasting is required and storage systems are required to smooth the variability. Second is material degradation. Blades face fatigue, erosion, and corrosion, leading to higher maintenance costs and downtime. Extending blade lifespan is essential for cost effectiveness. And third is grid integration. It becomes complex as wind penetration rises. Managing frequency, voltage, and balancing requires smarter electronics and system design. The fourth is environmental impact, which persists, including bird strikes, noise, and visual effects. Mitigating measures such as smart sitting and shutdown on demand radar systems are emerging. Finally, economic variability, while costs have fallen, capital intensity and financing remain hurdles, especially in developing markets. Example include in California, where curtailment of renewables due to grid limitation is significant. So, and in North Sea, where saltwater corrosion challenges turbine durability. So, recognizing these issues helps frame where innovation must focus on. Coming to next generation technologies. So this slide here showcases on one hardware side where we see lighter composites, biomimetic aerodynamic designs, and floating offshore platforms, and modular turbines. So floating concept like high wind in Scotland and wind float in Atlantic, they have already demonstrated this. Uh, their demonstration sets a feasibility in deep waters. So once considered, which was an inaccessible. So now in digital technologies, AI-driven predictive maintenance and digital twins are transforming the operations. For example, Vestas uses advanced analytics to reduce downtime and boost the efficiency by 20%. And the third is system integration, which is equally critical. Smart grid connectivity, hybrid renewable systems, and advanced storage and grid forming capabilities are making wind a stable backbone of power. So in Australia, a Hornsdale Power Reserve demonstrate how renewable and advanced storage can provide grid stability traditionally supplied by the fossil fuels. So nowadays, the system is so advanced that we can actually mimic the power supplied by fossil fuels by using renewables. We'll see how combined energy system storage can contribute better to the adoption of renewables. So if we see the market trends and projection in India, India is world's fourth largest wind power market now, with massive potential still untapped. So ambitious target include achieving 50 gigawatt of wind capacity by 2030 as part of the national goal of 500 gigawatt of non-fossil capacity. So policy drivers such as competitive bidding, repowering projects, and production linked incentives are accelerating deployment. So production linked incentives, nothing but PIL, is one of the schemes which motivates Make in India. So in Ola Electric also, we produce vehicle in-house, we produce batteries in-house, we produce motor in-house. That is why Ola is awarded with this PIL scheme. So in the similar way, in the wind technology also, when you produce, the condition is something like when you produce more than 50%, 60% of your materials in-house, you get eligible for that. So these schemes encourage the manufacturers in India to produce more wind turbine technologies. And offshore potential is also being explored. Tamil Nadu and Gujarat have identified strong offshore wind resources. So international investors are showcasing some keen interest in India. So both as a huge market and as a manufacturing hub. So the sector is also attracting R&D and partnership. For instance, Suzlon is leading in Indian wind manufacturer and is innovating lighter turbines adapted to India's wind profile. Meanwhile, Adani Green Energy is also investing heavily in this hybrid wind solar projects. So these trends highlight that India's dual role in expanding domestic deployment while positioning itself as a global clean energy player. So let's just discuss what are the advancements in blade design and materials used. So blades are the most critical components in the wind turbine, and innovation here drives major performance gains. So carbon fiber composites reduces blade weight by almost 25%, enabling longer span with greater fatigue resistance. For example, LM Wind Power, a company has developed 107-meter carbon blade for offshore turbines. And coming to aerodynamic optimization, through computational fluid dynamics and wind tunnel testing enhances lift to drag ratio, so which contributes to aerodynamic optimizations. And coming to smart materials, so smart materials can have a shape memory alloys and piezoelectrics, which allow blade to adapt geometry in real time, improving performance under variable winds. So for a real world example, Siemens Gamesa is using recycled blades, which integrates advanced resins for sustainability, while General Electric's Halide X, which is the largest capacity wind turbine existing today, use ultra long blades built from advanced composites. So let's just discuss about carbon fiber composites and how do they contribute to our wind turbine. So carbon fiber represent a revolutionary in blade technology because it makes the wind turbine blades lighter. So compared to traditional glass fiber, carbon fiber allows 25% weight reduction and also 40% cost saving over blade's life cycle. This enables a longer, stiffer blade without requiring a proportional increase in the tower size. So Sandia National Lab has demonstrated that carbon fiber composite will significantly improve fatigue resistance, extending blade lifespan from 20 to over 30 years. So manufacturing advancements such as resin transfer molding, which reduces the production time by over 40%. So in practice, these blades are already in use. LM Wind Power's carbon fiber blades are which are equipped in General Electric's Halide X offshore turbines are currently among the largest in the world. So which are producing about 12 to 14 megawatts of power. You can imagine what is the scale the wind power has reached today. So by lowering the material fatigue and reducing the cost in the carbon by using carbon fibers, so this becomes a commercially viable project. These advancements highlight how material science directly impacts both economics and performance in the wind sector. So as I discussed before, biomimetic blade designs. So basically, we see the solution revolves around our nature itself. So we get inspired by the nature. So nature has long been the source of inspiration for engineering. And in wind energy also, one example is that humpback whale flipper, which is a design which has tubercles, bumpy ridges, and which reduces the drag and increases the lift. So which can be applied to wind turbine blades. This design can improve power output by almost 16 to 30%. Sandia National Labs and multiple startups have tested prototypes with promising results. And there's another concept of all feather serrations, which are another inspiration. Owls fly silently because fine separation along their wings. So when applied to wind turbine blade trailing edges, these reduces noise by almost 3 to 5 decibels while maintaining aerodynamic efficiency. So Siemens Gamisha has experimented with such designs to reduce the community noise impacts. So these nature inspired solutions reduce the shortcomings of the wind turbine, which is something like noise and bird hitting and increasing the lift profile of the turbine blades. So another nature inspired design is maple seed geometry, where the seed spins and auto rotates as it falls. So, which has inspired small turbine designs with improved startups in low wind condition, which is called as a cut-in speed. And this could also help microgrid and distributed energy applications by learning from the natural adaptations. Engineers are enhancing efficiency, reducing noise, and expanding where turbine can be deployed. So biomimicry offers not just incremental improvement, but entirely a new way to think about performance and sustainability. Coming to vertical axis wind turbines. So vertical axis wind turbines, one sidelines are regaining its attention. Unlike horizontal axis wind turbines, vertical axis wind turbines capture wind from any directions. So eliminating the need for yaw mechanism and reducing the mechanical complexity. So this makes them specially suited for urban environment with turbulent wind patterns. So recent advancement have improved their efficiency. This is a helical 7 years design now achieves 35% higher efficiency than older Darius configurations. So vertical axis wind turbine also operate more quietly and pose lower risk to bird population. So basically the design does not include horizontally revolving blades. So this technology finds its own application in urban areas where the power can be generated. But unlike horizontal axis wind turbine, where it cannot be deployed in such areas, so this is a very simple approach which can be deployed in areas where bigger turbines cannot be deployed. Coming to floating offshore wind platforms. So offshore wind resources are immense, but many lie in water too deep for traditional fixed bottom turbines. So floating platforms solve this challenge. So we need not anchor the turbine to the bed of the sea using a concrete or a structure. So they anchor to the bed of the sea using cables. So these are some of the floating offshore wind platforms which contribute to the wind power generation. Why we are going to offshore is because the wind is more powerful, stronger, and consistent in the offshore regions. So this is a region where we have to focus on. So some of the semi-submersible platforms with the 3-column designs are stable in harsh seas and borrow heavily from oil industry experience. So basically, the oil industries use their rigs on the platform in the sea. So they are very stable. Using that kind of approach, nowadays there are floating wind turbines, and tension leg platforms are used to dot the mooring lines to minimize the motion. So basically, the waves are enabling the this tension in the leg platform. So what we are doing is we are moving the platform and correcting based on the tidal waves. And spray buoy concepts. So with deep cylindrical ballasts achieve stability through a lower center of gravity. So to coming to a practical example, Equinor's Hywind in Scotland, the world's first floating wind farm, has been operational since 2017, delivering power to over 20,000 homes. Similarly, another company, Windfloat Atlantic from Portugal, has shown excellent performance in 100-meter deep waters. So coming to smart turbine control systems. So as turbines grow larger, smart control becomes essential for reliability and efficiency. So advanced sensors are required, which now monitor vibrations, blade stress, temperature, and wind conditions in real time. So data streams feed into the control system that optimizes the performance dynamically. And sophisticated algorithms adjust pitch, yaw, and rotational speed to maximize the power capture while minimizing the fatigue. So another approach is predictive response system, which is often powered by machine learning, which anticipate the wind changes before they actually occur. So adjusting the turbine setting proactively. For instance, General Electric's Halide, which I discussed, the world's largest wind turbine, which operates offshore turbines, also employs sensor-rich platform that adapts pitch and yaw with remarkable precision. So similarly, Vestas is also integrating smart control algorithms to minimize structural stress while maximizing energy yields. So let's just see what is the role of AI and machine learning integration in the wind power sector. So artificial intelligence is transforming wind energy. So AI-driven systems improve operational efficiency by up to 20% through smarter controls. So machine learning algorithm enable predictive maintenance, cutting down time by about 30%. Neural network process diverse data streams, wind speeds, vibrations, power output to continuously fine-tune the turbine performance. So deep learning models can even predict failures a week in advance, so enabling a proactive repair. So we are getting a lot of data from these wind turbine sensors, and we can apply these deep learning models to even predict for the faults which are yet to happen. So for example, Vestas uses AI platform to forecast the maintenance needs across its global fleet, while Siemens Gamesa is also using AI for optimizing the blade pitch control. So AI also improves forecasting accuracy, unlike the traditional approach, with energy production predictions, which is now 15% more precise. In India, Tata Power is also piloted some AI systems to integrate wind forecast with grid operation, reducing the curtailments. So this integration turns wind farm into an intelligent data-driven assets. So as AI advances, it will be central not only to turbine optimization, but also to grid level management, ensuring renewable and stability is at scale. Next, see how these predictive maintenance technologies are coming into picture. So predictive maintenance is becoming a cornerstone of efficient wind operations. Nowadays, this predictive maintenance is also getting into electric vehicles and every other equipment we see around us. So there is a lot of data which is coming from the sensors, which is uploaded to the cloud and which is processed. So even this AI models can predict much before that even the sensor or some device gets faulty. So condition monitoring systems, these use sensor to track the vibration, temperature, and acoustic, detecting early signs of wear. And data analytics evaluate historical trends to forecast optimal maintenance intervals, preventing costly failures. So AI optimized scheduling, which reduces cost by 20 to 35% while maximizing the availability. So performance optimization tools, which extend the component lifetime by identifying the operational adjustments. So, for example, DNVGL, it is a company which uses predictive maintenance platform, which are now widely used in Europe, which helps operator extend turbine availability beyond 98%. So in the US, Next Era Energy applies predictive analytics so across its vast fleet to save millions annually. So in maintenance cost also it saves a lot. So predictive maintenance is shifting the industry away from reactive repairs to a proactive repair. So data-driven management, which reduces the downtime, lowers the cost, and ensures higher output over turbines' lifetime. Coming to advancement in power electronics. So power electronics is one of the backbone of wind turbines, which integrates into modern grids. So wide bandgap semiconductors like silicon carbides and gallium nitrides, which are enabling higher efficiency and compact converters. So nowadays, we have seen how compact the mobile chargers have become. So thanks to the silicon carbide and gallium nitride based devices, wherein we are able to operate at higher switching frequency and reduce the component sizes. So these advanced converter topologies such as modular multi-level converters, which improve power quality and also reduce harmonics. So and grid support functions, which support voltage support, frequency regulation, and fault right through, are increasing in the embedded, which are increasingly embedded into the turbine electronics. So, for instance, Hitachi Energy and ABB are advancing in SiC-based converters that reduce size as well as losses. So, offshore projects in Germany now deployed modular multi-level converters to stabilize the grid and integration of large farms. So, these innovations ensure that wind penetration grows, power electronics maintain the grid stability while improving the efficiency. Let's now see what is grid forming inverters. Grid forming inverters are revolutionizing how renewables integrate with grids. So they allow wind farm to behave like virtual synchronous generators. So providing inertia and stability traditionally supplied by the fossil fuel plants. Fault ride through, which is a capability which ensures that turbines stay online during disturbances and improve its resilience. So, and there is one more concept of black start capability, which allows wind farm to restart grid after a outage. And once it was thought impossible for renewables, now it is possible. So, for example, in Australia, the Hornsdale Power Reserve, backed by Tesla Technologies, has demonstrated how inverter-based system can stabilize the frequency. So, as I discussed, now wind farms act like a virtual synchronous generator. So, this technology is a game changer. It reduces dependence on conventional plants and allows renewables to take the leading role in the grid stability. Coming to modular turbine designs. So, modularity simplifies turbine construction, transport, and maintenance. We'll just see how it will aid the construction, transport, and maintenance. So basically, nowadays, the blades are segmented, so which can be assembled on the site, enabling ultra long blades, so without the logistic bottlenecks. So basically, we see these wind turbine blades going one after another on the highways. You might have come across convoy of many blades. So as you see, this is a very challenging task to transport to the site. So segmented blade simplifies the assembly, which can be assembled on the site itself. Next is prefabricated tower sections, so which also reduce crane requirements and accelerate the installations. Coming to another segment wherein which will aid this construction is modular drive trains, which allow for a rapid replacement and upgrade during the turbine life cycle. So these are the three sectors which enable us to develop the wind turbine at the site itself. Coming to ultra high capacity turbines, as I said, the turbines are reaching tens of megawatt range. So now this modular turbines simplifies turbine construction and transport and maintenance, as I discussed earlier, and are able to achieve multi-megawatt capacity. So turbines are now reaching unprecedented scale. So current leaders include General Electric's Halide X, as I said, and Vestas V236, which are rated for above 15 megawatt. So you can imagine one turbine generating 15 megawatt of capacity. So this in turn leaves us with the cost advantage as well as powering multiple of homes using a single turbine. So these next generation prototypes are targeting about 20 megawatt with rotor diameter exceeding 280 meters. So these turbines reduce cost per megawatt nearly by 50% as fewer units are needed to achieve the large scale capacity. So for example, this single Vestas V236 can power 20,000 European homes annually. So offshore wind farms like Dogger Bank, which is a company in the UK, are willing to deploy somewhere about 13 to 15 megawatt turbines, making it the world's largest offshore projects. So scaling capacity is not just about the size; it requires stronger materials, advanced logistics, and grid readiness. But ultra high capacity turbines are set to define offshore future and lowering the cost and maximizing the power density. So let's see what material science breakthrough can aid wind turbine adoption. So material science is a transforming in wind technology. So advanced composites, particularly carbon fiber, as I discussed in the previous slides, which reinforced polymers deliver enhanced fatigue resistance while enabling the recyclability, unlike the carbon fiber which was traditionally used. So this reduces blade weight and extends the lifespan of the wind turbine. High strength alloys like ultra tough steel and titanium composites, which are increasingly used in the towers and drive trains to withstand harsh offshore environments. So as I said, the opportunity in the offshore is huge because the wind speed is consistent and a lot stronger than onshore. So we need high strength alloys to withstand the fatigue resistant and use carbon fiber blades to achieve more power output in the offshore turbines. And as you know, it is the maintenance of the offshore turbines is very difficult. So we have to choose materials which will last longer. Coming to smart materials, including shape memory alloys and self-healing polymers, which are cutting edge, are under development. These can automatically adjust the structures or repair micro cracks, reducing the downtime. And coming to proactive nano coating, so coating the wind turbines will reduce anti-icing, anti-corrosion, and which will make the turbine hydrophobic, and which will in turn extend the component lifespan. So Siemens Gamesa has already developed anti-icing coatings in the northern Europe, keeping turbines operational during even severe winters. And for real world example, LM Wind Power is also one of the company which is piloting recyclable blade materials in partnership with Ørsted, a company which is addressing end of life challenges. So material science ensures that turbines are not only stronger but also more sustainable. So we have to recycle these materials. So now new technologies enables us to recycle this material and reuse again. Coming to aerodynamics and fluid dynamic advancements. So aerodynamic contributes a lot to the power conversion efficiency. So aerodynamic research delivers higher efficiency and reduce fatigues. So large eddy simulation, a kind of a model which provides detailed insight into turbulence around the rotor. So the improvements in blade element and momentum theory also increases the performance prediction accuracy by up to 15%. Wake interaction modeling, which also enables optimal wind farm layouts, boosting energy capture by almost 8 to 10%. So wake interaction is nothing but the trail, you can say shadow of the wind turbine. So when the wind crosses to the wind turbine, it undergoes turbulence, and there is a fixed length of rotor after which another turbine can be installed either behind it or else on the crosswind. So optimizing this wake interaction, which will increase the efficiency, and we can optimally lay out the installation of the wind turbine on a wind farm. So to maximize the output. And unsteady aerodynamic research, which will uncover how gusts and turbulence impact blade fatigue and noise. Bio-inspired flow control, such as micro vortex generators, which also reduces the drag and improves the lift. So in practice, the US National Renewable Energy Laboratory, which is NREL, which uses LES models, large eddy simulation, and also design better wind farm layouts. So using these models, as I said, wake interaction modeling and unsteady aerodynamic research, these will obviously aid the optimum installation of the offshore projects, so which are currently happening in North Sea, which employ wake modeling to optimize the turbine spacing and increasing its output. So these aerodynamic advances translate directly into higher yields at lower cost. Coming to structural engineering innovations. Structural engineering is very critical as turbines grow larger and larger. Advanced foundation systems like suction and gravity based designs are being developed to see varied seabeds. So these are very important and very crucial for the offshore turbines. And dynamic response control, including tuned mass dampers and active system, which reduces the vibration in the towers. Next is load mitigation strategies, such as individual blade pitch control, which will cut extreme loads by up to 20%, and structural health monitoring, which will have embedded sensor which track the stresses on the blades and structure in real time. So, for example, offshore wind farm in the UK are now employing suction foundations for rapid installation. And as I told, General Electric's Halide X, which is the world's largest capacity wind turbine, integrates individual pitch control to reduce the stress on the blade. So traditionally, we used to have pitch control on all of the three blades by equal amount. So by having individual control over each blade, we can optimize the power output better and resilient to wind gusts. So these innovation extend lifetime and reduces the cost and improves the safety while ensuring turbines remain resilient under extreme conditions. Next is digital twin technologies. What do you mean by digital twin technologies? This is nothing but a virtual model which is developed inside the laboratory to evaluate how a wind turbine will perform in the targeted environment. So digital twins are reshaping wind energy operations. So a digital twin is a virtual model which update in real time with sensor data. So high fidelity simulation predict performance under varying conditions, and predictive analysis forecast and failures before they actually occur, and optimizes the maintenance schedule. Virtual testing also allows operation to trial control strategies without physical prototypes. So, for example, Siemens Gamesa uses digital twins for fleet-wide monitoring, while NREL, which I quoted before, also developed physics informed twins to analyze the structural fatigue. So, digital twins enhance lifecycle management, cutting cost and maximizing the uptime. Uh, they turn turbines into continuously optimized assets. Let's just see how IoT and sensor integration benefit the wind turbine technology. So wind turbines now act as a Internet of Things. So basically, it is equipped with lot of sensors and also internet. So lot of AI models can make use of this data on the go and optimize the technology. So these sensor integration also use distributed sensor networks, so which can monitor vibrations, temperatures, and strain, and also environmental conditions. So edge computing process, which processes data locally and enabling fast decision making, and cloud analytics, which provide fleet-wide insights and optimizations. So, for example, Vestas has integrated thousands of sensors across the turbines, so feeding into an AI platform for real-time optimization. So these capabilities enable predictive maintenance, adaptive operations, and improved efficiency. So IoT ensures turbines are smarter and more connected than ever before. So let's just see what are the advancements in manufacturing and 3D printing, which are helping wind turbine technology. So manufacturing is undergoing a revolution with additive technologies such as 3D printing, which enables rapid prototyping of complex components. We have now seen rockets which are being 3D printed, so which enables us for a rapid prototyping, and we can also use complex shapes and make use of this technology for the deployment. And metal additive manufacturing, which produces lightweight, high strength parts, which are impossible with traditional methods. And on demand spare parts, which reduces the inventory cost and downtime. Topology optimization algorithm, which create design with 30 to 40% weight reduction while retaining the strength. Multi-material printing, which is also a technology which embeds sensor directly into the structure. For a real world example, General Electric renewable energy uses 3D printing for turbine components, while Siemens Energy also has deployed the additive manufacturing for gas turbines, space, and technology is also being adapted for the wind turbines. So advanced manufacturing also reduces the cost, accelerates the innovations, and enables smart turbines. Let's just see what is the application of nanotechnology in the wind turbine industry. So nanotechnology enhances strength, efficiency, and resilience. So as I said before, for the offshore turbines, we use coating which reduces the icing and formation of corrosion and whatnot. So nanocomposite materials like carbon nanotube reinforced polymers, which provide exceptional strength to weight ratios for the blades. So nanostructured coating reduces the ice, prevention of erosion, corrosion, and provides self-cleaning surfaces. So once these are coated with nanostructured coating, it becomes very easy to clean these turbines in the offshore. Energy harvesting nanostructures such as piezoelectric materials, which convert vibration into power for sensors, which is also being tested and deployed in the offshore applications. So for a case example, researchers at Fraunhofer Institute are also testing nano coating that reduce blade icing and load in the cold climates. Such innovations ensure turbines remain efficient even under harsh weathers. So nanotechnology bridges this material science and performance, unlocking new frontiers and durability. Now let's discuss what is the acoustic engineering solutions. So noise is a significant community concern in the wind turbine industry. So advanced acoustic measurements identify the sources of aerodynamics and mechanical noise, and acoustic designs such as serrated trailing edges reduce noise by 3 to 5 decibels. As I discussed in the previous slides, nature-inspired designs are also being tested, which reduces the noise level coming out of the wind turbine. Active noise control system, which adaptively cancels unwanted sound, which is just like the true wireless headsets we use, which cancels the noise. For instance, Siemens Gamesa is also using the trailing edge serrations to cut the blade noise, while the researchers in Germany are also piloting active noise cancellation for smaller turbines. This reducing noise makes turbines more acceptable near these communities, supporting the wider adoption. So you would not believe noise is also a concern in the installations because wind turbine produce a lot of noise. If a community is in the vicinity of these wind turbine farms, it is very disturbing to the community. So one of the sector in which the work is happening is acoustic engineering to mitigate these noises. Let's just see what are the environmental engineering synergies. So wind energy must align with environmental stewardships. So one is wildlife protection. So the systems using radar and cameras can also pause the turbines during bird mitigation. So one company called Ørsted employs such systems in offshore projects. So huge, like many birds come across the turbine, so which can be like the bird hit the turbines, and there are many accidents wherein the bird hit the blade, and many it is a hazard to the ecology also. So bird living in that area get affected, and we'll have to work towards how we can mitigate such hazards. So one of the approach is using radars and cameras, which can detect the bird hits, and ecosystem integration in offshore farms, which act as a artificial reefs supporting biodiversity. Soil conservation, which allows agriculture between onshore turbines, and minimal water use makes wind far more sustainable than thermal plants. Let's see how atmospheric science integrates the development of wind turbine. So atmospheric science improves the forecasting and performance. So high resolution weather models now achieve 95% accuracy, for 24 hours forecast. Mesoscale models provide resource assessment at 1 kilometer resolution, and LiDAR technology profile wind up to 200 meters in height, optimizing control, and boundary layer research, which inform wind farm layouts to minimize the turbulent losses. So you can see how a technology can improve the accuracy of prediction and also have an informed decision about the grid stability. So these technologies combined produces a very good system in place so that the wind forecasting is good and also the power coming out of the wind turbine is better. So for real world example, offshore farms in North Sea rely on LiDAR for accurate forecasting in the turbine alignment. So integrating atmospheric science ensures that turbine operate in the maximum efficiency while reducing grid uncertainties. Let's just see how data analytics and big data comes into picture. As I said, AI is also contributing more nowadays in terms of prediction and optimization of power output coming out of the wind turbines. So as I said, Internet of Things is enabling this big move in the industry. So modern wind farms generate terabyte of data daily. So thousands of sensors across the turbines measure these wind speeds, vibrations, temperatures, and power output. Managing this scale require advanced big data platforms. So analytics enable 99% plus availability as operators identify patterns leading to downtime before failure occurs. And predictive insights allow proactive maintenance and performance optimization, which improves the efficiency by up to 15%. For instance, the company Ørsted, which integrates this big data analytics across its offshore portfolio, which anticipates maintenance and optimizes scheduling. In India, Suzlon uses data platforms to improve this forecasting accuracy, so which reduces the curtailment losses. So the future is data driven, combining sensor data with weather forecasting and also grid conditions. Ensure these turbines and farms operate with maximum reliability and integration into an energy market. So this big data makes wind not only efficient but also dependable at scale. Let's come to cybersecurity for wind systems. As I said, wind turbines produce huge data, and when there is huge data over internet, there is cybersecurity issue. So as wind energy digitizes, so it also becomes vulnerable. So wind farms are now target for cyber attacks from state actors to criminals. So threats include control system breaches, data theft, and operation disruptions. So multi-layered protection is essential, and we need to encrypt this data and network segmentation and also intrusion detection. So compliance frameworks such as NERC CIP in North America and IEC 62443 globally sets this cybersecurity standards for industrial systems. So real world cases have shown that the risk in 2022, a cyber attack on a German turbine manufacturer disrupted thousands of remote connection to turbines. So such incidents underscore the vulnerability of turbines and importance of resilience. So by safeguarding these systems, operators ensure continuity, protection to investments, and also maintain public interest and trust in this renewable infrastructure. So cybersecurity is no longer optional. It is the core to the wind energy's future. So let's just see how adoption according to climate have been done in wind turbines. So wind energy must adapt to increasingly extreme weather conditions. So design for extreme wind condition ensure turbines withstand hurricanes and blizzards. We might have seen many turbines falling apart due to extreme weather conditions. So, for example, General Electric's Allied X offshore turbine, so which is engineered to survive Category 5 hurricanes. So you can see the level of commitment the General Electric engineers have in designing for these extreme case scenarios. So thermal management is also a concern. Thermal management systems enables operation from minus 40 degree to plus 60 degrees. So Siemens Gamesa cold climate package are widely deployed in Canada and North Europe. Coming to adaptive operations, so which integrate weather forecast to adjust turbine performance in real time. System resilience, which is enhanced through redundancy and fail-safe mechanisms, which ensures continuity even under stress. So these strategies are critical for regions already facing climate change impacts, from typhoons in the Japan to heat waves in India. So climate smart designs ensure that wind energy remains reliable even in the challenging worlds. Let's just discuss what is this extreme weather resilience. So resilience strategies are increasingly embedded in turbine designs. Pre-storm preparations. So systems automate this protective measures 48 to 78 hours in advance. Next is storm survival mode, which locks the rotor and adjusts structure to reduce the damage. So typically a wind turbine locks its rotor and reduces the lift produced by the blades by adjusting its pitch. Next is post-storm recovery system. So uses drones and sensors for rapid condition assessments and damage mitigation through advanced materials and which reduces the repair cost. So in Japan, typhoon-resistant turbines are also being piloted. So with reinforced blades and towers, offshore like Equinor integrates storm survival protocols into floating platforms. So these measures reduce downtime, cut repair costs, and protect the infrastructure. So extreme weather is inevitable. We cannot control the weather at all, but resilience ensures continued operation throughout. So let's just see how wind resource mapping affects the wind turbine technology. So accurate resource mapping is the foundation of wind turbine projects. Satellite-based measurement provide global data sets with about 1 kilometer resolution. Ground-based LiDAR systems, which captures the local wind up to 300 meters. Nowadays, machine learning models combine these data sets for better prediction accuracy, and high resolution modeling, which accounts for terrain and micro scale patterns. So, for example, India's National Institute of Wind Energy has developed wind atlases to guide project sightings. Similarly, Global Wind Atlas, developed by World Bank, which provide open access data worldwide. And advanced mapping reduces this investment risk, ensures optimal siting, and also maximizes the project yields. Let's just see how climate change affects and impacts these assessments. So climate change will reshape the wind resources. So as we can see in this graph, so projections show higher average wind speeds in some regions, while others may face declines. Storm intensity is expected to rise, requiring stronger designs. So long-term assessment integrates climate models with wind resource planning. For instance, European studies show Northern Europe may see higher wind availability, while the Mediterranean regions face greater variability. So these insights shape infrastructure investments. Developers are now assess not only today's wind, but how resources may shift over, let's just say, 20 to 30 years. So this ensures projects remain viable across their lifespan despite this changing climate. So let's just see how we can integrate this weather forecast. So weather forecasting is integral to the wind turbine operation. So real-time data ingestion, which also combined with satellites, radars, and ground stations. Ensemble forecasting, which uses multiple models to provide probabilistic predictions. Power production forecasting, which converts weather data into expected generation. Next is operational optimization, which allows proactive scheduling of maintenance and grid integration. For example, Spain integrates this wind forecast into national grid planning, so ensuring supply demand balance. So in India, state load dispatch centers use this short-term wind forecast to minimize the curtailment. So forecasting bridges the meteorological and energy, which makes the wind reliable for grid operators. Let's see how seasons affects this and how we can optimize wind turbine according to the seasons. So wind output varies seasonally, requiring adaptive strategies. So winter operations use anti-icing systems and cold weather packages. And in the summer operation, deployed enhanced cooling and dust mitigation. In the spring and autumn transition, which provides a window for maintenance because the wind is less, and year-round monitoring, which tracks the seasonal performance and inform adjustments. So in the real world, Siemens Gamesa employs anti-icing systems, and while Indian wind farms adopts dust mitigation strategies in arid regions. So seasonal optimization ensures turbine remains efficient in all climates, maximizing the annual output. Let's just see how multi-hazard design work in wind infrastructure. So wind turbines must withstand this multiple hazards. So we'll see how they are affecting. So seismic resistance, so which is achieved by base isolation and flexible foundations, and hurricane survivability, which relies on aerodynamic reinforcement. So as I said, now variable pitch system is used for the individual blades. And coming to flood resilience, which involves elevating the electrical components and sealing the enclosures. So, for example, Japan is involved in higher seismic activity. So their offshore projects integrate seismic and typhoon resilience, while in the US, Gulf Coast turbines are designed for storm surge protection. So multi-hazard designs ensure these turbines are safe and reliable even at high-risk regions. Let's just see infrastructure hardening. So hardening infrastructure improves resilience and safety. So how we can have infrastructure hardening is by having enhanced foundation, like deep serration provides stability in the extreme seas, reinforced towers with high strength steels, which reduces fatigue and vibrations. Then protected electronics, which resist electromagnetic pulses and surges. Then backup systems, which provide emergency power and communication. So offshore turbines in North Sea now deploy some foundations and redundant backup systems to withstand harsh storms. So hardening ensures the turbines are not just productive, but resilient to the infrastructure capable of surviving these harsh wind conditions and extreme events. Let's just see what would be the emergency response systems if one of the uh, hazard or event is detected. So emergency response capabilities are critical for modern wind farms, so which include automated shutdown systems, which can stop the turbine within seconds when dangerous conditions are detected, and emergency communication networks, which maintain this connectivity during disasters, which ensures this coordination with the grid operators and the local services. Drone-based assessment, which can quickly survey this wind turbine conditions after storms, so reduces the time and risk of manual inspection. So drone-based approach is taking off very quickly nowadays. Even the blade inspection is done through drones, and even the cracks in the towers are inspected through the drones, unlike the manual assessment. Next is remote monitoring platforms, which enable off-site management during crisis. So, for example, Ørsted is a company which integrates drone into inspection across its offshore portfolio, and which also uses real-time monitoring, which centers in Spain to manage these emergency events. So, with climate risk rising, emergency response system also protects these assets and safeguard personnel and enable rapid recovery of these systems. Let's just see how we can integrate this climate modeling into wind turbine technology. So wind planning is increasingly integrates into global and regional climate models. So IPCC scenario guide long-term energy planning. IPCC is nothing but Intergovernment Panel for Wind-based Applications. So it's an international body which guides how long-term energy can be planned. Next is regional downscaling, which produces site-specific projections for wind speeds and weather extremes. Next is extreme event analysis, which identifies risk like stronger storms and drought conditions. Next, uncertainty quantification, which ensures resilience even under multiple climate features. For example, European utilities now use downscales models to assess offshore wind viability under future climate conditions. So integrating such insights ensures investment remain robust across decades. So let's just see what is the risk assessment framework in wind turbine. So risk assessment ensures project account for hazards and vulnerabilities of the wind turbines. So first step is like hazard identification, which catalogs threats like storms, floods, and seismic events. Next is vulnerability assessment, which analyzes turbines and system weakness. Next is probabilistic quantification, which combines hazard frequency with consequence severity, and mitigation strategies, which develop cost-effective countermeasures. For instance, offshore projects in Japan now employ seismic risk modeling before foundation design starts itself. So these frameworks ensure that developers make informed choices and minimize financial and operational risks. Let's just see what is the adaptation pathways. So adaptation is not a one-time action, it evolves in stages. So 2025 to 2030, which is an incremental improvement in such anti-icing coatings and modular repairs and better forecasting of wind data. And coming to 2030 to 2040 decade, we'll see deployment of advanced materials, predictive maintenance systems, and integrated hybrid renewables. And in the next following decade, 2040 to 2050, we'll see fully climate adapted systems with revolutionary technologies like recyclable turbines and autonomous wind farms. For example, Denmark's energy agency has already mapped adaptation strategies through 2050. So linking its innovation policies. So adaptation is a pathway which ensures resilience, which keeps pace with climate change. Let's just see how we can integrate into a smart grid. So wind energy is increasingly supporting the smart grids. So advanced metering, which enables real-time monitoring and demand management, and demand response system, which balances the supply and consumption dynamically. Next is grid services, such as voltage support and spinning reserves, which come directly from the wind farms itself. Next is predictive control, which integrates forecast into grid dispatch. So Denmark is a global leader. Wind regularly supplies more than 50% of its electricity while maintaining grid stability through smart integrations. So this slide demonstrates how wind is not just energy generation, but an active grid participant. So we'll see the application of in the microgrids. So wind also powers resilient microgrids. So community microgrids, which provides local energy and security. So these community microgrids are nothing but smaller turbines which are installed, let's just say, in the urban areas. Next, island nation, which like Hawaii and Mauritius, which reduces dependence on diesel with wind and solar storage systems. So by integrating the storage systems and using wind turbines, we can mitigate this diesel-powered generators which are providing energies to the island nations. Next is industrial facility, which use microgrids to cut cost and boost the reliability. Then military bases, which adopt wind-powered microgrids for operational independence. Nowadays, the airborne wind turbines also coming, which are not having structures, which are kite-based wind turbines. So they can be portable and also can be deployed in the places where wind energy is not accessible and installation is very difficult. So real world example like in the Kodiak Islands and Alaska runs largely on wind hydro microgrids, so reducing diesel imports dramatically. And microgrids highlights how wind energy supports both sustainability and also resilience. Let's just see how we can store this wind energy. So energy storage systems, which complements wind's variability. So wind is not blowing all the time, and it is also a seasonal component. So battery storage, such as lithium ion, which provides fast grid balancing. Nowadays, bigger modules are coming, just like the wall from the Tesla. So which is used to store the energy from the renewables and provide whenever there is a peak happening in the grid. Next is pumped hydro, which offer large scale and long duration storage. So whenever wind turbine energy is available, so water is pumped into a higher region, and whenever there is a need of power, this is converted into hydropower and which can be used as a battery. So and next system which uses storage is compressed air systems. So we compress the air by converting electrical energy into mechanical energy, then which delivers the cost-effective bulk storage. And next, we use turbines to convert that energy back into electrical energy whenever we need. And then there is green hydrogen, which enables seasonal storage and sector coupling. So we convert uh, uh, water into hydrogen gas and we store it and we convert into electricity whenever it is needed. And there is a European company which is developing a project which demonstrate wind to hydrogen at scale. And in Hornsdale in Australia, which couples wind with Tesla batteries, as I discussed, for frequency stability. So this storage ensures wind energy is firm and dispatchable, ready for 24/7 supply. Let's see how grid stability solutions can be coming from wind technologies. So grid stability is essential as renewables expand, and frequency regulation is one of the main important component. So in India, we have one grid, one nation policy, wherein we have one grid with swings in together. So frequency regulation is very important, which uses advanced inverters to provide synthetic inertia, and voltage support, which comes through reactive power control, black start capability, which allows farm to restart dead grids. So Hornsdale Power Reserve in Australia, which has shown that how renewable plus storage system can provide this grid services faster and more effectively than fossil plants. Even the fossil plants require a time period to start and supplying power. So by having wind turbine with storage solution, we can start the grid instantly by using cutting edge technologies. So grid stability solution redefine renewables from variable suppliers to grid stabilizers. Next, we'll come to hybrid renewable systems. So hybrid systems combine complementary resources. So we combine some other renewable with wind energy system so that our system is more reliable. So primary combination is wind and solar hybrid, so which ensures continuous supply as the sun and wind peak at different times. So when the sun shines stronger, uh, we'll store that energy, and also we combine with the wind energy, which can also be accessed throughout the day with variability. We combine these two technologies and integrate with the battery for smoothing out these fluctuations. So battery integration is very essential. Next is backup generator, which add redundancy. So in case we don't get wind power, then we have a redundant, which is a backup generator. So in India's Gujarat, hybrid park is a landmark. So integrating 30 gigawatt of wind and solar with storage in one location. So such project maximizes the land use, lowers the cost, and delivers reliable and clean power. So next we will see what are the key findings of this presentation and what are the future directions and key takeaways from this. So we conclude this with some key takeaways. So technology readiness, which is a next generation wind technology, already shows 20 to 40% performance gains with commercial deployment, which expected in this decade. Next is climate adoption. Turbines are being engineered for extreme weather and ensure resilience. Next is system integration. So wind is evolving into cornerstone of smart grids and hybrid systems and circular economy. So recyclable blades and sustainable materials, which will address the end of life cycle changes. So most importantly, interdisciplinary innovations is the main engine behind this progress. So combining engineering, science, and economics to make the wind energy climate smart and climate resilient and sustainable. So projects like Dogger Bank in the UK and Highwind in the Scotland and in the Hornsdale in Australia, they illustrate the future is already here. So a task ahead is to accelerate, scale up, and to adapt. So by combining the AI tech in the industry, we can forecast the wind better and which ensures better energy production and advancements in aerodynamics, which ensure the aerodynamic efficiency, and also resilient to hurricanes and extreme wind condition, which also increases the lifespan of wind turbines and become climate ready. So I would like to sincerely thank AICT Training and Learning Academy and for sponsoring this important faculty development program and R&D cell of Regent Education and Research Foundation groups for organizing with such a dedication and vision. So it has been a great privilege to share my insight on next generation wind turbine systems as part of Green Horizon. Alongside distinguished faculty and experts, I'm especially grateful to Dr. Suman Jana, convener of this FDP, for his support and extending this opportunity to contribute. I also wish acknowledge the organizers, coordinators, and the entire team for their tireless effort. And thank you so much again for this opportunity. If you have any questions, please let me know. Thank you.
Thank you, Dr. Castellino, for your excellent talk. We'll now open the floor for question answer session. So I would request the participants to kindly ask the questions or write in the chat box. We'll forward the questions to our speaker.
Good evening, sir. So,
Hello, good evening.
I have a question, sir, regarding that floating wind turbines. So,
Yes.
sir, according to my knowledge, there is no operational floating wind turbine in India, but in globally there are some.
You are
So,
correct.
my
Yeah.
question is, sir, what are the challenges and some problem having in India to install floating wind turbines in deep water, sir?
Excellent question and excellent monitoring of this presentation. So basically, India has a huge potential. The potential is already assessed by the agencies, Ministry of New and Renewable Energy. You can also see online there are reports being generated, and the main challenge is the cost and the policies. So basically, offshore wind turbines are cost heavy. You can say there is a huge capital required to build these farms, and also policies which are required to enable faster deployment of these technologies. So in India, policies are underway so that the offshore wind turbine can be deployed. But there is a lot of opportunity in India. But you are right. Until today, there is no wind turbine in the offshore. I think we'll see soon. Who will be the first? We'll see. Yeah.
Yes, sir. Thank you, sir. Thank you so much.
Yeah. Welcome.
Uh, there's a question from Manjuna D. The question is, can we use thermoplastics and bio-based composites to reduce cost and blade life?
Okay. So my answer is I'm not expert in this field, thermoplastics and composite materials. So nowadays, carbon fiber is used primarily for the blades, which strengthen it mechanical strength and which will long laster than fiberglasses. And for the structure, I don't think any challenges as such is there. Maybe research will help in identifying the difference between the traditional materials or using bioplastics. So we'll have to see how it compares to the traditional method and also to the new technology which you're talking about. But I think I'm not I'm the not the right person to answer in this field. I'm really sorry.
Thank you, sir. There's another question from C. Viswas. The
Yeah.
question is, what can be superior in renewable energy, wind or solar or hydro?
So you are just asking the first child is better or the second child. It doesn't work that way, right? So everybody is a children of this energy. So you cannot say one renewable is better than another. One finds its own application. Let's just say the solar is very good when the sun is shining. Even though solar energy is having very low conversion efficiency, we find its application, and in India we have already developed. And also there is wind turbine. If you see in Tamil Nadu, Coimbatore area, there are a lot of wind turbines which are powering the nation. And as you said, hydro is also one of the major. So we have to combine these renewable. One sector cannot alone supply this energy to the grid, because renewable is the main problem with renewable is its variability. So we have to combine, maybe use a storage solution so that we get a solution to this variability. That is the main goal behind developing renewable technologies and combining them.
Thank you, sir.
Yeah.
There's another question, but from C. Viswas only. So,
Yeah.
but sir, wind energy cannot be installed everywhere, but solar energy
Right.
can be.
You cannot say solar energy can be installed everywhere because of the terrain conditions and whatnot. So wind turbine, so solar, if you see, the energy production per area is less as compared to wind energy. Okay. So wind energy can capture more energy, like let's just say one big turbine of 13 megawatt can be installed in a very less area than a solar park with 13 to 15 megawatt of energy production. So each have their own merits and demerits. So solar is used in highly shining areas in Gujarat and other part of the nation, while the wind turbines find their application in mostly in Tamil Nadu and other part of the nation. So you cannot say like the solar can be installed everywhere and wind turbine cannot. We have to combine. That's why there is a concept of microgrid and smart grid in this particular context. So basically they combine goodness of solar and also the wind. So wherever in a region, let's just say more wind is blowing, we can have more wind turbines installed over there. But in the region where solar is dominating, we cannot have a wind turbine over there, and we have to install solar. You cannot simply conclude that solar is better than wind or wind is better than solar. So it depends on the geography and the data. So as I discussed earlier, so we have a lot of data related to region. What is the wind and irradiation particular to that region? So combining this data will have the informed decision so that the investors can invest better in terms of solar or wind. I think that answers your question. So, are there any further questions?
Yes, sir. There's a question from Suraj. The question is it efficient to integrate solar and wind energy harvesting?
Okay. I don't know any metric to support my answer to you. But solar and wind provide this variability issue. Basically, wind is blowing mostly after the afternoon time, 4, 5, 6, up till 7, 8 p.m., where sunlight is not there, and solar cannot generate even a kilowatt hour of energy, while solar can generate about 6 hours of daylight, and it can capture. So energy is not something which is consumed equally. So let's just say in the morning there is a peak, and in the evening there is a peak in the household or residential areas, and in the industries in the daytime it is peak. So energy demand is not proportionate to the energy provided by these renewable sources. So that is why we combine the technology, the goodness of both. We store the solar power in the batteries. It is one of the approaches I'm talking about. It need not be solar energy stored always. It is given to the grid also. So in modern farms, the solar farms, the power is directly feeded into the grids using inverters, grid tied inverters. And application wherein solar and wind are combined, they also use energy storage solutions wherein they store whenever the solar output is coming, and also they integrate with the wind turbine so that this variability factor is ruled out, which can also be integrated into the grids, microgrids, and can have a stable operation. So in terms of efficiency, I'm not sure what efficiency you're talking about, but the efficiency factor always comes into the conversion of the irradiance into the power output. And in terms of wind power, it depends on the how fast the wind is blowing, based on the seasons, based on the climate condition, and many factors. So integrating them is always a good thing, but efficiency wise, I'm not sure how it will benefit.
Thank you. So there's another question from Dr. Pritish Banerjee.
Yeah.
What types of fatigue testing are used in live prediction?
Okay. According to my knowledge, I have come across, they use LiDAR based technologies. They use fatigue testing. So basically, the material is tested using modern LiDAR technologies. So I have been to one conference. In fact, it is happening right now in Bangalore, the Electronica, wherein modern optics are being exhibited. So wherein they are using light-based applications, which detects crack formation and fatigue testing, and many more emerging technologies are upcoming, which are modern in terms of AI and machine learning, which combine multi-sensor data to analyze whether this fatigue load will occur based on the wind data conditions or based on the climate condition also, before even they occur. So primarily the cutting edges today is light-based applications.
Thank you, sir. There's another question from C. Viswas.
Yeah.
Are there any other types of wind energy harvesting system exist other than the tower type, that is a vertical axis wind turbine or horizontal axis wind turbine? Something very
Very
new
good.
and innovative.
This is a very good question, because I was already working on my PhD on this. So as someone pointed out, this wind turbine cannot be installed anywhere. You are absolutely right. It depends on a lot of seismic activity evaluation and area evaluation. And now if you see, engineers are looking for higher hub heights and higher rotor diameter, because wind is blowing more consistent, stronger and consistent at a higher altitude. So engineers are always seeking to go higher and higher to trap that high altitude wind. So you are right. There are technologies which are not using only horizontal axis wind turbine. There are airborne wind turbines, which are basically airfoils flying in the sky. So the air blowing through them is generating lift, just like you can imagine an aircraft which produces lift by using the pitch of the wings. So that lift is converted into a pulling force of the thread, and that thread is connected to a ground station and which is coupled with the generator to generate electric power. So this is a relatively new technology. The research has been happening in 2 decades, and there is a commercial company, not in fact 2 or 3 commercial companies which are deploying 150 kilowatts of this airborne technology, where a flying device is there which is trapping this lift in the air and converting into rotational energy. So the advantage of this technology is this can be deployed in inaccessible areas or isolated island countries, island nations, and also untapped areas where wind is more consistent in the higher altitude, right? You can easily reach that altitude and trap that wind power. So airborne technologies are also emerging, and we will soon see maybe 500 kilowatt and up to a megawatt probably. And you won't believe, even people are looking for Martian applications as well. So in the upcoming future, maybe by 2030, SpaceX is launching a Martian space mission. So probably we'll see some airborne wind technology, because they are more lighter than solar panels, right? So the weight matters to a spacecraft. Maybe this is another discussion some other time. Yeah, that is what the potential of wind energy is.
Thank you, sir. There's another question from Dr. Debashri Shaha, GNIT. The question
Yeah,
is, in West Bengal, wind speed is very less. Which type of
yeah.
wind turbine will be suitable here?
So basically, wind turbine is planned and deployed based on the site survey, wherein first geographical data is taken into picture. If we see National Institute of Wind Energy, wherein we can see a lot of data at 100-meter hub height, 200-meter hub height. Maybe it is not available at 100-meter height, then we'll have to increase the hub height. If you are asking me how we can deploy, then maybe going up higher altitude is one of the solutions, or else wind energy is not applicable to that. The current technology using horizontal axis is not applicable to that region. We can also explore technologies, as I stated, flying kites which can trap this wind, high altitude wind, and take advantage of the stronger and consistent wind at above 500 meters from the ground. So wind is always stronger and consistent as you go higher. So I would see airborne device which can be deployed in regions like that.
Thank you, sir. So due to time constraints, we cannot take any further questions. So if the participants have any further questions, we'll direct to sir, and the
Yeah.
message will be forwarded to you. So thank you, sir, for your presentation, which not only highlighted the latest advancements in wind technology, but also shed light on the challenges and innovations shaping the future of sustainable energy. From the role of digitalization and AI in optimizing wind farms to the exciting developments in optional floating turbines, your talk truly opened our eyes to what lies ahead in the renewable energy landscape. We are grateful, sir, for your expertise and the clarity of your explanations and your passion for driving the change in the energy sector. Thank you, sir. Thank you for your talk, sir.
You're welcome. Thank you for the opportunity. Yeah.
Thank you, sir. So we'll further move on to the next session.
Okay.
Thank you, sir. Dr. Niba Rani, madam, are you there?
Yes,
Uh,
sir. Hello. Sir, am I audible?
Dr. Niba Rani, madam, Hello, madam.
Yes, sir. Am I audible?
It's audible, but the voice is actually the audio is very minimal.
Okay, wait. I'll
Can you,
try.
ma'am, just increase the volume, ma'am?
পরীক্ষার
Am I audible now?
Yes, ma'am. If the sound can be more, please, ma'am, it will be like it is very less.
So is it okay now?
Yes, ma'am.
Hello.
Yes, ma'am. Hello.
Sir, my voice is clear now?
It's clear, but it's still now somewhat low, madam. Is there any microphone or something um, you can use?
Now, check the once.
Yes, ma'am. Can you hear us?
Yes, sir. Yes, sir.
So let us start today's session. You welcome Dr. Niva Rani, Assistant Professor, Electrical Engineering Department, currently serving at VNIT Nagpur, who will discuss on emerging and innovative methods to integrate wind energy system with grid. So first, let me introduce our speaker. Dr. Rani earned her PhD in electrical engineering from NIT Silchar, focusing on reactive power reserve management in conventional and wind integrated power systems. She holds an MTech in Power System from Amity University and a BTech from RVSCET Jamshedpur. She has published SCI and Scopus papers, authored book chapters on renewable integration and microgrid energy management, and is an inventor of a South African patent on hybrid prediction system. So, madam, thank you so much for being with us today, and you can start. The stage is yours, ma'am. Thank you.
Is my screen visible, sir?
Yes, ma'am. It's visible. It's visible.
A very good evening to everyone, and thank you for joining this session on emerging and innovative methods to integrate wind energy systems with grid. My name is Dr. Nibha Rani, and over the course of this presentation, I'll take you through how wind power is one of the fastest growing renewable energy source and how we can integrate it to our existing grid. We will also explore its current status and the challenges and innovation in this direction. Further, we'll go for future direction. What are the future direction works that are making wind energy integration more reliable and sustainable? This will be the content, the flow of my today's presentation. First of all, I'll be dealing with the introduction of wind energy, its importance, and how it is growing, and then status of wind energy, status in global arena, as well as from the national perspective also, how we Indians are being contributing to this green energy thing. And then uh, we'll be talking about grid integration and then we'll be linking this wind power to the existing grid, and also seeing after this I will be seeing the challenges related to this grid integration, as and here we'll talk about the technical thing, the technical constraints on economical challenges, and also the regulatory challenges what are being there in the system if we want to integrate wind to the existing uh, grid. And this whole thing will then open the stage for discussion on the innovations that are being done in this field, and the innovations are being talked like on the basis of converter and control innovation, where we'll be talking about the advanced inverters, packs, and grid code. And then how this hybrid system with storage are contributing to the challenges, like are mitigating the challenges. We'll be talking about this, how AI and digital tools are helping to mitigate the challenges related to whatever we have talked before. And then at last, we'll be having a glimpse of offshore wind and HVDC transmission, how they are supporting the grid wind integration in grid. And then at last, we'll be dealing with some policies, some case studies of different countries, and the future trends to be opted in order to make this grid integration more faster, like wind integration to the grid more faster and sustainable. Now coming to the introduction, the global transition of low carbon economy has made renewable energy more important than ever. The Paris Agreement and the other international commitments have placed energy transition at the center of its climate action. And in this, wind energy has emerged as one of the most promising solutions. And why wind energy has evolved? Because of its scalability and its cost effectiveness and ability to provide large amount of clean electricity, unlike fossil fuels. Also, it could be harnessed on massive scale, and this highlights that this wind energy is not a it's an integral part that has effort in offering effective solution and effective solution in meeting the rising electricity. For meeting rising electricity demand while reducing the emission, and which is our target in any of the low carbon economy or the Paris Agreement. Now coming to the global status. This global status basically it shows if we look at this graph, we can see that total global capacity has exceeded to 1174 gigawatt. It's like we are approaching to 1 terawatt generation, and this has reached, and with 121 gigawatt is being added in 2024 itself. Like every year we are integrating large amount of share and large amount of wind share in the grid. And we can see, like when we'll analyze the data, we have seen that 87 gigawatt is being integrated from China itself, and this has raised the 70% of new global capacity. Like entire capacities, 72% has been installed by the China only. And from here, we can see that this diagram show that China is the major producer of wind energy. Like they are exploiting wind energy to the fullest as compared to other. Still, a lot of things are going on in China to further integrate more wind energy to the grid. And this is the global scenario. Now coming to India's capacity, from like as on 31st March 2025, the report from MNRE, it has seen that the from India has reached to 50.4 gigawatt installed capacity, wind power capacity. And with this, it has been ranked at fourth globally in terms of total installed capacity, and trailing behind China, US, and Germany. State-wise, we have Gujarat, Karnataka, and Tamil Nadu as major producers of wind energy. And like by geography also, India has a potential. India has like not only like India has a huge potential to generate electricity, and it is capable of providing at least 18,000 megawatt wind energy annually. Offshore, its potential can be analyzed. Offshore also, it like nowadays uh, offshore works are also going on, and this estimate that Gujarat has 34 gigawatt and Tamil Nadu has 35 gigawatt of offshore capability, and lot of things are going on to further enhance the offshore capability. Now this is the data. Now coming to why grid integration is important. Initially, like we are having the capacity to generate like 50 megawatt and everything from wind itself, and we are harnessing wind energy so as also to in order to properly utilize this, we have to integrate it to the grid, because we nowadays from traditional approach, grid is the only thing that grid is a medium through which we used to get energy. Hence, grid integration is very much essential with large scale generation of anything like solar, wind, hydro. But and with grid integration, there comes a lot of variabilities also, like technical aspect is there, economic aspect is there, regulatory practices are there. So as various like multiple types of sources can coexist, basically coexist, because they have conventional has different nature, wind has different nature, solar has different nature, and we have a grid as a combined medium which integrates all these variabilities into it and supply us power in a very reliable and efficient way. Hence, lot of technicalities, regularities are there. From this diagram, we can see that nowadays we are capable of integrating wind energy at any level. Like if we are having more offshore group, we can integrate wind energy at transmission level. Onshore group could be incorporated at sub transmission level. And if we are having like as decentralization is being on progress, so we can also incorporate small turbine group at primary distribution level. Hence, this wind energy has got a huge like huge aspect in this grid integration. We have to look into everything because huge potential of energy, and we can also harness it at different levels subject to our requirement and subject to the development also. Now comes why this integration is important. This integration is important not only to like to follow the rules, but also to have optimal use of these renewables. Without proper integration, most of the like if you're generating in excess amount and then you want to sell it, like, and for selling you want to come to the medium which will further sell it to the uh, sell it to the consumers. So you have to integrate it to that medium, and hence grid integration is very much essential for maintaining, for optimal use of renewables, and for earning, for having economic efficiencies. Now when comes grid uh, integration, we must talk about the stability in the system, because everybody is having different nature. For a system to coexist, they must follow certain rules or certain them to have the stability. We must have some balancing thing. So for that, this maintaining power quality and stability is essential. And like when we are going for grid integration, by incorporating the technical issue, basically we try to have this power quality and stability management. From there we used to maintain frequency, voltage, and LVRTs and other stabilities. Now, this grid integration, like with the huge potential of solar energy, this wind supports decarbonization goal, which is already there in the Paris Agreement, that will go for net zero carbon emission. And with this, like, if we'll promote the grid integration, this decarbonization goal will be reached. Further, this grid helps in having the flexibility and resilience of the system. And for this, we try to maintain stability by, like, if we are talking about decarbonization, we are basically talking about we are basically talking about going from conventional to this green energy thing. And for this, we need, for the past decades, we are dependent on conventional things, such that they are like everything are designed as per the conventional norms. And now these renewables are coming, they have variability, so we have to maintain a balance, so that the stability of the system is not disturbed. Now comes the key challenges. These are the basic like overview of the challenges. As I have already said, it's not only the technical challenges, there are economical challenges also, there are regulatory challenges also. So these are some of the challenges. One by one, we'll be dealing with each of the challenges, and I'll be talking why this happens. Why, like, if I'm talking about variability and intermittency, I'll be talking about why it is there in the system, and how it can be, like, and what works are done to overcome this challenge. So it's not about dealing with the challenge only. I'll be proposing solution with that also. Once covering with this all challenges, we'll be moving for some new emerging techniques that are being there, which are further enhancing grid, further like promoting grid integration in the system, and while covering these challenges into account. The first one is variability and intermittency. Variability, as the name suggests, it is basically the natural fluctuations of renewable over the time. However, intermittency is a period, like this to a different term. However, people use it as a synonym, but they have different meaning. Variability is the natural fluctuation, and intermittency is when the resource is not available. There is no, like, we cannot say not available in case of wind. That is not enough to have generation. So that is intermittency, or that is not enough to be felt. So the variability and intermittency are the inhibition or the inherent property of the any renewable sources, and with wind also it is there. And because of this variability and intermittency, when coming to the grid aspect, we are seeing that there is a gap between supply and demand, and this has to be matched every second. And this variability and intermittency, which is bit unpredictable, like predictable to some extent, always there is some slight error. So because of this, it makes this balance, which is must have in a grid. And then variable, since this are like this is unpredictable, so variable output most of the time overload or underuse the transmission line, making it to be congested. Next, this variability and intermittency can be handled by accurate forecasting and geographical diversification of wind farm to call out small weather effects. Now, when I'm talking about forecasting, we need to know for what reason we want what kind of forecast. Like forecasting is done basically for certain time scale, and also it and usability also. Like if we are talking about the real time dispatch, so we have to go for 5 to 60 minutes time scale. The forecasting should be accurate for 5 to 60 minutes. And if you're going for day ahead scheduling or hour ahead scheduling, then we could make this time horizon to be 1 to 6 hours ahead. And for planning, we do have unit commitment or market trading. Economic dispatch, the forecasting is for day ahead time. The time horizon is of day ahead. And for like resource planning or contingency, this planning is this time horizon is of a long time, because for having any kind of like if you want to have any kind of new installation, you have to know the you have to plan everything ahead. So for that resource planning, we always go for long term planning. And now when we are talking about forecasting, apart from time zone, we are having different approaches also. Like nowadays, AI, ML based approaches are also there. But going by this, we are having deterministic approach, which is like now a time is being redundant. Now we are analyzing everything with uncertainty, and with uncertainty we are having a probabilistic approach, we are having risk index, we are having scenario based approach to predict how wind will be there, like to predict wind. These are some approaches, and nowadays a lot of efficient approaches like based on AI and ML are also used for forecasting. The second very much important thing for grid integration is reactive power and voltage support. Basically, these are stability related things, as voltage is a very important factor in electricity. If we are not having adequate amount of, like if our voltage gets on reducing and reducing, and if it will reach to voltage stability, and prolonged operation of this voltage stability may hamper the may lead to blackout in the system, and proper voltage is very much essential in the system. This has given rise, like voltage support is basically with deregulation also, this has become very much demanding, because with deregulation nowadays everybody wants to earn money, and for that they used to operate those apparatuses at they used to overuse that apparatuses, and they are and such prolonged operation, if you will be overusing it and you will be using it for more time, then it hampers the stability of that system, basically reactive power of that system. And as reactive power in a system is very much like strongly related to voltage support, hence in order to have both proper voltage in a system, we have to have proper reactive power in the system. When I'm talking about reactive power, we shouldn't be ever be get confused it with real power. It is not the real power, because we are not going to use it. It is, but it is required in the system to establish, like to energize the entire circuit or to establish electric and magnetic field in the system so that the real power can flow smoothly. Hence, it is there in the system. However, we're not using it, but it is there to maintain stability in the system. Now coming to why it matters. These wind plants are often located at far centers. Long transmission lines are there, which is connecting wind farm to the grid. This long transmission lines basically incurs high reactive losses, and this deteriorates the voltage at the load end. Hence, this is very much essential to look after this. And also, when coming to the modern wind turbines, we are having various power electronic devices coupled with the generators. We are having various wind turbines coupled with the various power electronic devices coupled with the generators, and these power electronic devices are basically they are not supplying reactive power, and they are supplying reactive power minimally till now, unless they are specifically controlled, or else they have no control, no supply for the reactive power. However, they are consuming it. So this power electronic devices has introduction of this power electronic devices has added as a sink of reactive power, which further causes voltage dip, reduction in reactive power that results in voltage dip. Now coming different ways to manage it, how reactive power could be managed in the system and how voltage support could be provided. First of all, we could go for wind turbine converters. There now, earlier I have said that this nowadays a lot of power electronic converters are there with wind generators to and they are capable, like they are not they are capable of supplying reactive power, but they are not supplying, like because they are not tuned to supply that. So we can go for the ways, like still research are going on. Lot of papers are there on how this DFIG could be incorporated in a system, and in need how it could inject as well as absorb reactive power dynamically. Also earlier there were like this allows to use this doubly fed induction generator as a turbine integrated STATCOM kind of device. Further, we are having capacitor bank and shunt reactors to support reactive power at the grid side. Then then STATCOM and SVC are there at the point of coupling of large integrated wind farm to provide voltage support, and the response time for this is very millisecond, because and that is essential. And also in many countries the grid code is there, this wind plant should maintain certain amount of power factor while injecting to the grid. And this is one of the example how like local compensator can enhance the voltage as power is coming from long distance. Like the voltage is getting deteriorating as the distance increases. However, if the compensators are optimally placed, it could give support and it will enhance the voltage profile of the system. Now coming to frequency regulation. Earlier, frequency was maintained by the synchronous generator. These were having high inertia. So high inertia, so they resist the frequency variations also. But now with this integration of wind energy and solar, this has become low inertia, and there low inertia has came into the picture, and this turbines, like they are affecting the frequency. They are not able to resist the frequency change. Further, the primary response, the plant droops their output when the frequency falls. But with wind farm, this is not naturally occurring unless it is programmed to do so. Also, fast ramping, like in case of surges, this fast sudden drops and fast surges are there in wind. that causes frequency deviation. And for this, we need an other device with integrating in coordination with this wind to correct this ramping rate. Then comes reserve adequacy. We must have sufficient amount of reserve to handle the variability in the power on and the frequency. And for this, the mitigation measure, we could go for synthetic inertia, like program wind turbine converters to release kinetic energy during frequency drift. For this, we can go for connecting a flywheel or supercapacitor with that, which would act as a synthetic inertia, which would provide synthetic inertia to the wind farm. Then we could go for fast frequency response. For this, battery storage or inverter-based resources could be providing action so that there will be like the response could be faster enough. We could also go for enhancing grid code where the primary and secondary control can participate. Proper forecasting is one. Everything could be solved if we are having accurate forecasting, but accurate forecasting is a myth. We are always approaching to that. And even if we'll go for approach, even we will forecast, we are not able to have such a like versatile dynamic system. It's a big challenge. So we have to look into that also. These are some of the mitigation measures for frequency regulation. Now comes fault right to. Earlier, conventionally, it was with the renewable, it was the ability that whenever there is sudden voltage drop or voltage surge is there, these renewables get disconnected. However, but nowadays, as renewables share is increasing day by day, and if we will go for this disconnection thing, this will result in like this may destabilize the system. Whenever there is fault, earlier if there was a fault, this renewables used to get disconnected, but now we cannot disconnect the major sharing major shareholder from this, because this will destabilize the grid. Now this is challenge because these are the converter based turbines, because every wind generator are basically converter based turbines and are very sensitive to voltage disturbance, and it will sense disturbance so aptly and act accordingly that it shows LVRT and HVRT. Plus this protective relays and power electronic devices are designed to avoid this kind of tripping. And how this fault right through could be achieved? It could be achieved by controlling the algorithm in converter. It will limit the current and maintain reactive power injection during the fault. Then this will support the voltage during the fault, and hence it won't allow the system to trip. Also, if we are having some DC link energy storage, which will support during power imbalance inside the converter, then also this problem could be get rid of. Coordinated protection so that turbines don't trip off before the grid recovers. It should give certain amount of time to recover. From the figure only, you can see that this is like a turbine should have at least 1500 millisecond time given so that the grid recovers. This is what LVRT like how LVRT performs. Then also we have to we require grid code, strict grid code with this. Every turbine should follow this grid code compliance, where they should give proper voltage time profile so that the grid can reestablish itself and system can operate reliably. Now, apart from the technical constraint, there is a physical constraint also, that is transmission constraint. Since these are located at far end, sometimes this transmission line are having insufficient capacity to incorporate huge amount of energy into it. which causes congestion. Also, the existing infrastructure is not fast enough to apt for to like to adopt this decentralized renewable thing into the system, which lead to curtailment of like due to the limited infrastructure. Sometimes with wind, we do have capacity to generate wind, but due to from the stability point of view, we are forced to curtail to meet this to like eradicate this congestion, and this also causes voltage and stability issues as it is traveling through the long distance. Now this transmission control constraints not only causes revenue loss but also the transmission loss, huge transmission loss, and it increased curtailments like demotivates the investors to invest in this and further invest in the upcoming renewable energy targets. So it is anyway delaying the renewable energy targets and the projects. And mitigation strategy should be, we should go for green energy corridors. We should build new transmission system which could be capable enough to incorporate this new large share of green energy coming from wind. And this dynamic line rating, we could use real-time weather data to safely increase the existing line capacity. We should go for upgrading substation, adding more reactive power compensating devices there, and also co-location of storage. So as this, there should not be differ in transmission upgrades. They shouldn't differ for the transmission upgrades. Now, what is curtailment and revenue loss? Curtailment is basically when the utility has ability to generate power. However, from the grid management side, due to congestion or due to some other activities, system stability related issue, grid has decided that no, we won't take power from this, and hence you shouldn't generate power. So this basically rises like we are not able to sell the power. However, we have ability to generate this. This is basically curtailment, and this occurs losses. It's a kind of opportunity loss. You have the opportunity to earn money, but since the system is not stable enough to integrate your to provide you opportunity to have the revenue, so it instructs ki no, we won't take, and hence you are having opportunity loss kind of thing. And it happens because one of the thing is transmission congestion. The other thing is oversupply. Suppose more generation are there during off-peak times, so we are having more generations, then obviously those renewables, we cannot integrate more supply as the demand is less. Also, sometimes to maintain frequency and voltage, operators are being instructed to reduce the wind output, and this basically results due to forecast error also. Now, impact on revenue. Actually, due to this curtailment, wind developers get paid only for the deliverable energy, like whatever. It is a fact, but you will be get paid only for the delivered product, not what you are holding. So similarly, wind developers are not get for potential energy. They are incurring losses. Further, this frequency curtailment reduces the capacity factor and return on investment, and there is no compensation on curtailed energy. Or in some countries, however, there is partial compensation is allowed, but still this anyway incurs revenue loss. This could be mitigated by better transmission planning, by having green corridors and HVDC integration. We could have efficient transmission system which can incorporate a large share of wind, and hence it could be integrated to the grid. Then we must we could go for flexible demand. If we will classify demand, and we could go for flexible demand, so as during this time, whenever there is opportunity to earn revenue, they could absorb the excess energy instead of curtailing. This is one of the way to mitigate this. And obviously forecasting is a thing, like it will improve forecasting and align scheduling with the actual output. Then also one, like if the market is designed in a such a way, because we are going for net zero carbon print thing. So if the market is designed for such a thing that the priority is given to the renewable, then also the system could be like this curtailment and revenue loss could be mitigated. Now, apart from this, there are several economic barriers also. Wind farm itself has a very high initial capital cost. It requires efficient, costly generators, transmission upgrades, and store is also required, which is an upfront investment. This These are the things. However, when we go for offshore are even more costlier, because we need a strong foundation, cabling, operation and maintenance, logistic, and everything. Apart from this, grid connection cost. Many a times, this wind power developers often have to pay for the substation, grid studies, and connection fees. Like they have to go for this also, because the infrastructure is not apt till now, and there is long distance to the load centers, which add expensive transmission lines or HVDC links. Further, this wind is uncertain, and hence the revenue earned by this is again we cannot say volatile. It's again uncertain or variable. So this basically affects the like whoever is funding the wind, whoever is funding this wind power integration or wind. Basically, these are affecting the investors. Sorry, basically these are affecting the investors. Since the revenue earned is also volatile, so they are being reluctant to invest in this, and they too they won't go for investment unless there is long-term power purchase agreement. Further, apart from this, there are some hidden costs with this wind power integration. They are the ancillary services, because they require proper balancing, they require spinning reserve, they require battery storage, they require reactive power support. These all the hidden costs again add as the cost of ancillary services. Hence the lenders and also sometimes these lenders apply highest rates to or require large equity share for variable output project, and these are some of the barriers. One second. These were some of the challenges. Now coming to some advanced methods, how this is being how this converter, what are the things that are emerging techniques that are being there to integrate wind to the grid. Till now, we have gone to the conventional challenges and the conventional way of handling that. Now comes some advanced techniques. The first one is, since this entire wind grid integrated wind energy system is based on converters, so converters matter in the system, and we could go for different controllers or different designing of converters, so that we can harness more and more amount of energy in the system. Now these converters are basically in wind turbine are a link between generator and the grid. basically decouple the mechanical part to the grid side, to the static part, like the rotating part to the static part, and hence it allows the rotating part or the mechanical part to generate more, to rotate at variable speed and harness maximum energy from wind. And then this converters maintains everything, like converts the thing into proper apt voltage and frequency, and then it is being injected to the grid. Apart from this, it also provides active and reactive power control. It also maintains the fault right through. It also filters the harmonics and provides synthetic inertia during by momentarily releasing the kinetic energy. Now, what are the converters innovation till now? Converters basically convert earlier grids were there, like grids decide the grid is being operated to work at certain voltage. So wind power has to be reached to that voltage and then to be injected to the grid. But nowadays grid forming converters are there. They basically set the voltage and frequency instead of just following the grid. This basically allows the converters to, like, this basically allows the wind farm to act as a virtual synchronous machine by providing inertia, voltage, and support. Apart from this, various converters with battery storage or supercapacitors enables ultra fast active and reactive power support. Also, since now they are setting voltage and frequency independently, they have ability to start the grid, start the dead grid. Like they have capability to start from the black start, and it also smoothens the wind power output. Also, various modular multi-level converters are used in offshore and HVDC system to which for better scalability and fault ride through and fast action also. Now coming to other like silicon carbide and gallium nitride switches, basically shrink the size of the converter size and also enhance the switching speed, which further improve the efficiency and reliability in the system. And this multi-swing converters and parallel paths further help the system to have fault tolerant and redundant design. This increases the uptime and reduces the operation and maintenance cost of offshore wind farms. Now coming in depth with this grid forming inverters only. This is what I have, like in the previous slide only I have said. These are basically these basically have the ability to synchronize with grid voltage and frequency, and they have, because they can establish frequency and voltage without an external reference, they can energize the dead grid section and start the restoration process after the blackout. And now coming to synthetic inertia. As wind penetration increases, synthetic inertia has become important for frequency stability through this basically provides whenever there is, like with synthetic inertia, whenever there is sudden drop in frequency, this synthetic inertia or inverter based resources is able to inject extra active power within a fraction of a second. This mimics the immediate energy release as from the spinning reserve and act as a synchronous machine inertia. It's like it mimics the behavior of synchronous generator, which is having inertia. Since this is very fast and provides energy for like small amount of time, so it could help momentarily, and like it could buy time so that the other resources could come into picture and then support the grid. So it is also there that where converters are being programmed in such a way that it will provide synthetic inertia control to the wind integration. Basically, this in a way enhances the grid stability with high share of renewables and complement the primary frequency control. Now coming to other advanced control strategies. Now there are model predictive control, which predicts the future grid condition over a short horizon. It optimizes the converter or the farm output proactively, improves ramp rate, voltage support, and fall through. Also, this adaptive group control dynamically adjusts the frequency, power, and voltage depending upon the grid condition. It enables the wind farm to behave as a synchronous machine without overreacting. And this distributed control of wind clusters basically enables the coordination between the wind clusters, like wind farm clusters, and this coordination basically improves the reactive power, frequency support, and curtailment minimization and in the system. Now, apart from this, there is FACT devices for integration. FACT devices, as we have seen that this reactive power support or proper voltage support is needed before grid integration. So for that, we are having STATCOMs, SVCs in the system, like they are being integrated with the wind farm before introducing the power to the grid. There is there so that it could have, when it will be introduced to the grid, it could support the voltage also, or have optimum amount of reactive power, so that can stabilize the weak grids. These are two diagrams how these are being like introduced to the wind integrated system just before the grid integration. There is at the grid central, there is STATCOM there. In the second one, there is SVR is there, and these converters are there, which is taking care of voltages and everything, and the reactive support, auxiliary reactive support demanded by these things are being supplied by the STATCOMs. This basically, in case of weak grids, compensate the voltage dips, maintain power factor, and damps the oscillation. It also helps wind plant to meet the grid code requirement of reactive capability and fault right through. And also it reduces the risk of voltage collapse that could result in blackout. Now comes grid code compliance. Grid code, till now we have seen that lot of technicalities are there whenever we are talking about the wind power integration. One is reactive power control, voltage control, active power control, frequency control. So for everything which challenges the stability of the system, we must have some grid code requirement for that, so that this variability in the system could be turned to the uniformity. This grid code is very much essential. Grid code is basically discipline that is to be followed before injecting power to the grid. And for that, the grid codes are basically related to low voltage right through, high voltage right through, inertia for frequency response, and then reactive power response. This basically grid code basically varies from countries to countries, and this variation of grid code basically further challenges the turbine developers or turbine developing companies, because they have to make their turbine in such a way that it should follow the grid code norm of the country, which is again a challenge. So harmonized requirement of grid code is necessary. And and also it is also needed for cross-border power market, where in which we aim to have wind energy trade. Now comes hybrid system storage. Hybrid system storage is there, like this variability of wind could be mitigated with by having some hybrid system where we can complement its variability with that. For this, we are having different kind of hybrid arrangement. First, with wind and battery energy storage system, where this basically whenever there is active and reactive power imbalance, this battery energy system provides active power support, and also sometimes it provides ultra fast active and reactive power for frequency and voltage support. It enables time shifting of wind energy to make the demand peak, and also it could absorb the excess energy whenever, like during off peak hours, like that revenue excess generation from the wind could be stored here and could be used during on peak hours. And the other arrangement is wind with other kind of renewables. It could be solar, hydro, biomass, which will be complementary to the generation profile of the wind to reduce the variability. Basically, this lowers the interconnection cost and also provides an opportunity to earn revenue out of this. And then there is wind plus hydrogen or thermal storage, which is able to convert the surplus wind energy to store, like we could from this kind of, we could store in a form of hydrogen or heat for later use, and could be add for long duration storage, like for smooth, like with batteries it is not possible to like have long duration storage, but with hydrogen or thermal storage it is we are able to have this long storage duration. Now this if we are going for hybrid system storage, we are easily mitigating problems like curtailment and congestion. We are enhancing the reliability of the system. Also, we have got this black start capability property, and it also helps to meet grid codes from ramp rate, reactive power, and inertia. Now coming to the hybrid renewable system, which is basically wind solar hybrid plant. It is wind and solar generation profiles are basically complementary. If you could find a place where we could have where we could harness optimum amount of wind energy during night and monsoon season, and during sunny season or during day we could harness solar energy, then this is very apt. Combining these two basically reduces the ramping stress of the grid and helps to meet the grid code by predictability and ramp rates. This is one of the picture shows one of the example of wind solar hybrid plant. With this, not only we are reducing the variability, but we are also sharing the land and infrastructure cost, because now we don't need extra to extra income to have separate wind and solar. Rather, we have clubbed them and use the existing transmission system or one transmission system to harness power from this farms to grid, and also lower permitting and environmental impact as compared to building these two plants separately. Some extra benefits are there. This type of structure basically supports higher renewable penetration without major new grid investment. Also, it improves project bankability and utilization of the transmission capability. Now coming to battery storage. With battery storage, basically Batteries can inject and absorb active power and reactive power in seconds and arrest frequency drops. It, it basically complements to synthetic inertia and program control. Also with battery storage during off-peak hour, if extra generation, excess power could be saved and which could be sold uh, during off-peak hours, or this further reduces, apart from this, during congested period also, this with this battery storage integration, we could save the excess generation, which could be further be utilized to have to generate revenue out of this. And one of the very famous project, Tesla Henderson Power Reserve in Australia, have demonstrated
Hello.
how large scale batteries. Yes, hello. How this large scale batteries can stabilize grid without reducing the operating cost.
Mr. Sandeep Bak, kindly mute your microphone. Requesting all the participants, kindly mute your microphone.
Now coming
Madam,
to
please continue.
hydrogen storage. Hydrogen offers a long time storage solution for renewable energy. Excess wind can be used to run electrolyzers which split water into hydrogen and oxygen. The hydrogen then can be stored in tank or pipeline and can later be used in fuel cell, or can be reconverted to electricity, unlike batteries, which are best for short duration operations. This integration of hydrogen further reduces the curtailment of high wind output period, creates a new revenue stream for selling green hydrogen, and enhances energy security and grid flexibility. Some pilot projects from Europe and Japan has already demonstrated how hydrogen can complement renewable to create a flexible and zero carbon system. Now comes supercapacitor and flywheels. While batteries and hydrogen address
Hello, madam. Are you there? Your voice is not coming. I think there is some technical issues at speaker end. Kindly be connected with us. She will join with us soon. Kindly stay connected with us. There is some technical issues at speaker's end.
okay, now I'm visible. I don't know
Yes,
where I
yes, yes,
lost.
yes. Yes, no issues, ma'am. Kindly continue.
Now, unlike hydrogen or battery, which are meant for providing support for short or medium time, like after a certain time, this this supercapacitors and flywheel have ultra fast balancing capacity. They could they the supercapacitor can deliver burst of power within milliseconds, making them ideal for smoothing momentary fluctuation. And flywheel, which store energy in its rotating mass, can inject or absorb power rapidly without degradation, and this could be done in uh, cycle of 1,000 times. Together, this technology, supercapacitor and flywheel, enhances the grid stability, uh, enhances the grid's ability to handle sudden change in wind output, and complementing the larger storage solution and improving the resilience of the system. Now comes pumped storage. Pumped storage remains to be most mature and wide used form of large scale energy storage. It works on pumping water uphill into the reservoir when the wind generation is high, and releasing it to downhill when downhill through the turbine to generate electricity when demand rises. This technology provides seasonal balancing, making it perfect complement to variable renewable like wind. In India, India has already significant pumped hydro plants potential, which could be modernized and expanded to support the higher share of wind generation. Now comes the second category of innovation, in which AI and digital tools have came into the picture to enhance the grid, like to support grid integration or to ease out the grid integration of renewables to the system. As we all know that artificial intelligence has transformed the forecasting scenario. Nowadays, machine learning methods trained on weather data, turbine performance, and historical patterns can predict wind output with higher accuracy. And this could range from short-term forecast to long-term forecast. That, like, through this we can predict from in the range of minutes to hours, which is very much critical for predicting grid stability. And with the day ahead prediction, also market operations can be dealt. As forecasting in the system has improved, there is no, like, this will again eradicate the need for backup power, saving the cost and reducing the emission. For countries like India, where renewable penetration is rising rapidly, AI-based forecasting is mandatory tool for integration. Now coming to basically how AI works. AI basically learns from and digests the weather data from the historical patterns, and then they produce the accurate prediction. And its performance could further be enhanced by proper training. And also the same thing which I have said earlier, that it does not only helps in giving us true picture of the wind power output from the variable source. However, it also eradicates the need for reserve power, which again lowers the operating cost and emission of the backup plants. Now comes predictive maintenance. AI and IoT measures are IoT sensors are being used to predict turbine failures before they occur. Vibration. temperature, and acoustic sensors detect these things easily from detect these things, and this machine learning algorithms analyze the data and identify the early warning signs. When these two are clubbed together, they could help they could enhance the they could schedule the maintenance proactively, and also it will reduce the downtime and cost and extend the turbine's lifetime. Predictive maintenance is especially valuable for offshore wind farms, where unplanned repair can be extremely expensive. Now coming to blockchain for energy trading. Blockchain technology is basically enabling new model for peer-to-peer energy trading. Consumer with rooftop solar and small wind can also sell their excess power directly to the neighbors through this blockchain platform. This reduces the transaction cost and ensures transparency, security in settlement. It's the basically market-based approach. In the larger market, blockchain can be the blockchain can streamline the renewable energy certificate trading, and this could minimize the dispute, reduce transaction cost, and allow instant verification of trades. Now there is another new thing. This is digital twin grid. Digital twin grid is basically a replica of a physical system. In this case, in the case of grid, for wind integration, digital twin allows operators to test different scenarios such as sudden wind drop or transmission fault without having the real world instability. This helps to basically plan a proper protective system and uh, train personnel, optimize operations from this. And this is basically one of the research, uh, digital twin grid is basically more useful for the research purpose, where you can plan expansion of the system, how the system will be, how system will operate, and how with this you can also plan your protection for cyber attacks, equipment failure, sudden fluctuations, and other. This kind of grid, like support with twin grid, basically enhances the resilience of the system. Now comes offshore and HVDC integration. Offshore wind basically provides both opportunity as well as challenge, as offshore offers sites for stronger wind and steadier wind, but leading to it basically enhances the capacity factor as compared to onshore location. However, less land use conflict avoid less. However, the challenge with the less land use capacity basically further add challenge to the system, and projects are being very much expensive. It requires special foundation, cables, and maintenance vessel. Despite of this cost, failing technology price, and policy support are the rapid reasons for the growth of this. One second. And the further challenge with offshore grids are basically these offshore grids are located at distant distant, remote places from the load centers. Hence, it requires like proper transmission system to transmit the energy from the load center, supply center to the load center. And for this HVDC came into integration. Conventionally, actually, HVDC suffers like HVDC allows bulk power transfer without with lower losses, especially with submarine cables. It also provides grid stability and flexibility, enabling cross-border renewable energy trade and better integration of variable wind energy. This is one of the example of this is one of the diagram of offshore wind farm. Here we could see that from this only we can feel that extra efforts have been done for this foundation and the floating structures, and for floating wind power again the cost becomes intensified. This for India, when we'll talk about India, for India, offshore wind in Tamil Nadu and Gujarat has potential to establish this offshore grid and diversify the energy mix, reducing the pressure on land use. Now coming to HVDC transmission. HVDC lines basically play a critical role in moving large amount of wind power over the long distance with minimum loss. HVDC suffers lower line losses and more stable for interconnecting remote and wind power with urban centers. Instead of this, HVDC offers hubs to multiple farms. Instead of connecting each wind farm individually, multiple offshore farms can be linked to common HVDC hub, and this will enable the efficient pooling of offshore wind resources before transmitting power to this hub reduces the infrastructure cost and enable efficient pooling of offshore wind resources before transmitting power to the shore. It also facilitates cross-border connection, creating regional offshore energy network. This is one of the diagram showing how HVDC transmission works. It basically transmits AC supply is being converted to DC at the converter station and then being transmitted, and then at the source station, it is from the inverter station, it is being inverted, again converted to AC and then fed to the distribution lines. Now comes floating offshore wind turbine. Traditional field bottoms are limited to shallow water, that is up to 60 meters. However, this floating platform allowed wind farm to be installed in the deep water location where wind speed are stronger and steadier. This extends the potential of wind resources, especially for countries with narrow continental shelves. Coming to the introduction of this, Norway's Hyndevine project by Equinor was the world's first commercial floating wind farm, providing large-scale viability. Japan also has multiple demonstration projects have shown that how floating platforms can withstand typhoons and seismic conditions. This pilot projects basically show global momentum towards scaling the floating wind as the cost continue to fall. Now coming to policy and regulation need. Effective policies are crucial for wind integration. Effective policies are crucial for wind integration, tariff support, such guaranteed grid access ensures the wind guaranteed grid access ensures the grid must evolve the requirement of modern turbines to provide grid support service like inertia and reactive power by aligning with such infrastructure and interconnection. Raises the wind capacity. Also, market reform should be added so that the supply curtailment, like wind supply curtailment, could be reduced, and revenue could be earned from this. Some examples of this, like for example, for tariff support on wind projects, UK's contract for difference scheme has significantly reduced the offshore wind price, or also India's wind tariff auction has enabled rapid capacity addition in this regard of incorporating wind. For guaranteed grid access, the European Union Renewable Energy Directive requires member states to provide guaranteed grid access, and China mandates priority dispatch for renewable in its power market, which is one of the things that will again open an avenue for a large share of integration through a large share of power through renewables. Now coming to after some policies, now we'll go for certain case studies of different countries. Now coming to Denmark case study, here the 50% of electricity is generated from wind, and it basically generates half of its annual electricity consumption from onshore and offshore wind, and strong government support, early adoption, and continuous investment in offshore wind help it to become a global leader in wind integration. Apart from this, this Denmark's electricity balanced with Nordic hydro import hydropower from Norway and Sweden. And this again emphasizes cross-border energy cooperation. Now coming to UK offshore success, like UK has the largest global offshore capacity, and it has installed capacity of 5 gigawatt. This has, for this strong focus on offshore has helped UK to meet climate target and strengthen the energy security. Contract for difference has been significantly reduced and reduced the levelized cost of offshore wind, making it competitive with the fossil fuels. And this scheme has created a predictable market environment, encouraging both domestic and international investment. Now coming to China's mega project, here China has been giant producer of wind energy. China has developed massive onshore wind based in its inner region of Mongolia and Gansu. Large-scale overhead projects are being expanded rapidly along the eastern coast, supporting the urban demand center. This mega project highlights China's strategy of concentrated renewable clusters for economies of scale. Further, this project of renewable energy integration of China has been intensified due to its other project, that is ultra high voltage DC line. China uses ultra high voltage DC transmission lines to carry huge amount of power from remote bases to distant load centers. And this is the upcoming project. This is the map for the upcoming project, where these are the solid lines are the planned HVDC lines, and the dotted lines are basically these are the operating lines, and the dotted lines are basically planned lines which are being operated. And this combination of huge this is one of the example where the combination of huge wind mega base and HVDC makes this China a global leader in renewable grid integration. Now coming to wind. In wind, there are like lot of projects have been developed in this wind and solar hybrid model, because geographically our country is having some areas of our country is having dominance on wind, and some areas are having solar. So if we could and somewhere we could also find somewhere we are having like coastal areas where we have optimum sun and wind also, which could be amalgamated together to generate hybrid project that combines wind and solar for consistent and cost effective generation. This kind of project basically increases reliability and reduces that intermittency issue. It is cost effective because of the shared infrastructure, and again the land use, dual energy generation from the same land. Some of the projects that Solar Energy Corporation of India conduct several auction of the has introduced several projects for integrating this hybrid model. And challenges with this are basically again the challenges are same: grid integration and energy storage needs. This ACCI has promoted several projects, like asked for several projects regarding this, because of the future prospect of India target to meet 500 gigawatts by 2030 through this renewables. Now coming to future trends, this future trends in this renewable energy or wind integration regard. When we look ahead, we are looking for 100% renewable ready grid, moving from partially integrated to fully renewable powered system. We aim to move from partially integrated to fully renewable system, and step by step these converters based or this new technologies or the shared hybrid models are basically increasing the are basically enhancing the integration of this renewable energy to the grid. It basically provides flexibility, large scale storage. It requires flexibility of large scale storage, demand response, and sector coupling. Countries like Denmark, Germany, and Portugal already operate with 70% of its generation, showing the feasibility. And to achieve this 100% renewable ready grids, what are the key enablers that are very much essential is strong transmission network, interconnector, and digital control. Now, apart from the 100% grid, there is hybrid. Now, when going from hybrid, nowadays we are having EVs, hydrogen coupling, wind. This basically provides flexible load. Like if we'll integrate wind with EV charging demand can act as flexible load, which will absorb the excess wind at night. And vehicle to grid technology enables EVs feedback to the grid. However, with hydrogen coupling, electrolyzers powered by excess wind convert electricity into hydrogen. Hydrogen can be stored seasonally and used for transport or reconverted to electricity. Wind plus hydrogen hubs are emerging in Europe, India, and Australia. Together, EV and hydrogen can create new demand centers for wind power, reducing the curtailment and improving economics. Now coming to the next, that is smart grid with AI and IoT. Basically, this artificial intelligence can improve in short time and ultra short time wind forecasting, and which will further optimize the real time dispatch and congestion management. It basically, and also it enables the predictive maintenance of turbine, reducing the downtime. With IoT, thousands of sensors on turbine, transformers, substation provide the live grid health data, and it facilitates self-healing grids that reroute the power during any kind of fault. And this digital twin model is basically virtual model of grid and wind farm that allows the operator to test scenario, reduce risk when when integrating higher share of wind energy. This is what we have dealt now. Now coming to the conclusion from the entire discussion, it has been seen that wind integration is essential for achieving net zero targets, and innovation in converters, storage, AI, and HVDC is making making this stable integration possible. Global collaboration and among policymakers and industry researchers is critical for success. This entire PPT has been made with these references. Thank you.
Thank you so much, ma'am. And it was really an informative and enriching session for all of us. Thank you so much again. So now we'll be having a very short question answer session from the
Sure.
audience. One question is there, ma'am, from
Yes,
Dr.
sir.
Pritish Banerjee, that if we look into global wind energy generation scenario, China
Yes, sir.
has the highest capacity compared to any other country. But if we compare it with India, what are the major challenges we are facing now to enhance our capacity, and how we can mitigate these issues?
One of the major challenge in India is what we face is with the government reform. If government provide, like in China, there are lot of efforts are being done on incorporating this renewable thing, and they are trying new avenues. However, in India, many a times you'll feel that project are being sanctioned, and then this uh, further, like we are not, it's basically failure from like management side. Sometimes we are not able to reach to that height. However, technologically also we are that much sound. We can also achieve that. There, if you would have given chance to do that at pilot stage, we can go for. But for large scale, again, lot of things come into picture that affects these things. Like, and this picture basically, these are basically from the government side, like not government, like local leader side, that basically harnesses. We have to change the mindset once and then go for this, then we can also surpass China someday. Because we are having everything, we are having proper land, proper irradiance, and we can have the places where we can have hybrid this solar and wind. But still we are lacking because of, I feel, because of this.
Yes, ma'am. Thank you, ma'am. And if there are any other question from the participants, they can ask. We are having very short time. So if you have any question, you can ask directly, unmute your microphone, or you can put it in the chat box. So I guess there is no other questions, ma'am. And thank you so much, ma'am, for being with us. It was really an informative and very enriching session. Thank you so
It was
much,
my
madam.
privilege, sir.
Thank you, madam. Thank you.
Okay, thank you.
And yes, ma'am. And that concludes today's day 4 session. Thank you to our speakers and all the participants for all your attention and joining with us. And we look forward to the day 5 focusing on industrial sustainability and AI in renewable energy. So goodbye and good night to everyone. See you tomorrow. Thank you again.